Hi students, it's Dr. Marks, and our topic for today is multiple regression. Now, as we've been discussing, regression analysis is a very powerful tool. It's a statistical technique used to determine if there's a relationship between variables. In other words, does variable X impact variable Y? And we're looking for a causal story. One cool thing is that we can measure the strength or the magnitude of that relationship. In other words, does X have a big impact on Y? Does it have just a little impact on Y? Is this a positive effect, a negative effect? But the advantage of regression is the ability to control for other variables that matter. So think about what we talked about with comparing sample means. We did smokers versus non-smokers with respect to age at death. And we said, look, there could be these other confounding factors. And we don't know if it's really because of smoking or because of other things. Healthy lifestyle, drugs, drinking, genetically disposed to certain issues anyway. With regression analysis, we can control for those other things. In other words, we can estimate these relationships and the magnitude and the strength of these relationships, holding all else constant. Now, we've been looking at simple regression, which means we have only one explanatory variable. Maybe we have test scores and they're explained by absences, or beer sales are explained by price. But here's the thing, while absences probably affects test scores and price affects beer sales clearly, there's other variables that matter. For example, if we're talking about beer sales, in a certain area, the population over 21 in that area would impact beer sales. But also the price of substitute for beer would impact beer sales. And we didn't control for these when we were just looking at price, right? So what we really need to do is called multiple regression, where we allow for control variables. Multiple regression employs more than one explanatory variable. So we might have a treatment variable of interest where something is specific, the thing we significantly, are interested in, and the other things might be control variables. But we don't have to have a treatment variable. So maybe I want to know, hey, does absences affect test scores? Well, another question would be simply, what affects test scores? So in one case, I have a treatment variable. In the other case, I'm just looking at control variables. In this case, what we're doing is estimating the partial effects. So basically the effect of absences on test scores when we hold all else constant. So when I say partial effects, we're really talking about isolating the effect of absences when we control for the other confounding factors that could also affect test scores. So when we say all else constant, it's basically like comparing students who are equal in every way except for absences. Maybe they're all economically disadvantaged and they have the same level of education and the same teacher quality and they go to the same school with the same quality and they're the same age relative to their grade. Now, I'm not saying that literally we have a data set where everyone's identical except for absences. I'm simply saying when we use control variables like economically disadvantaged and parental education, teacher quality, control for the school, in this way, we're holding those variables constant. Keep in mind, if it's not in the model, then it's not held constant. So I can take a whole group of very heterogeneous students and control for these variables and isolate just one variable at a time. So maybe I want to look at the impact of absences, controlling for economically disadvantaged and parental education and teacher quality, etc. Let's look at an example specifically related to beer sales. So suppose we have data that reflects sales per day for different mini-mart locations. Now, our original model had only one explanatory variable. We simply said that sales is going to be a function of price, and clearly price is an important variable when we're modeling sales. Now, the data we were using was for 18 packs. So let's say we have sales for 18 packs. But there are substitute for 18 packs, right? We've got 12 packs, we've got 30 packs. And so in theory, we know price of substitutes matters. So we should really, if we're trying to estimate sales for 18 packs, we should really control for the price of the substitutes, 12 packs and 30 packs. Now there are probably other substitutes that we should control for as well, but we want to keep it simple. So we're going to estimate the impact of the price of 18 packs on the sales of 18 packs, right? So price of 18 packs is going to affect how many 18 packs we sell, but we want to do this holding all else constant. And so part of our holding all else constant is going to be the price of those substitutes, 12 packs and 30 packs. So we need to expand our model by adding these two control factors, which now means we have three explanatory variables, right? We have price of 18 packs, which is going to affect the sales of 18 packs, but now we've added two substitutes, prices of 30 packs and the prices of, 12 packs. So these are all going to potentially impact our dependent variable. So I can write out an equation that looks like this. Sales of 18 packs is equal to, alpha is some intercept, which just moves our fitted line up and down. We've got beta 1, which is going to capture our coefficient related to the price of 12 packs, and beta 2 is going to be our coefficient related to the impact of the price of 18 packs, and beta 3 is going to be our coefficient related to the price of 30 packs. So what we're doing with regression is estimating alpha, our coefficient, which moves the line up and down, beta 1, which is going to be our partial effect, the effect of price of 12 packs on the sales of 18 packs, holding all else constant. Beta 2 is going to be our partial effect, capturing the price of 18 packs' impact on the sales of 18 packs, holding all else constant. And then same thing for beta 3, partial effect of the price of 30 packs, again another substitute, on the impact of sales of 18 packs, holding all else constant. And then we have that error term for the stuff that's not explained by those three coefficients. So part of what we want to do is think about the expected signs. What is the expected sign of beta 2? Well, the law of demand says if price goes up, sales decrease, holding all else constant. So if price of 18 packs goes up, we would expect sales of 18 packs to go down, right? So it should be obvious that beta 2 is expected, at least based on theory, to be negative. So based on this, what is our relative hypothesis test? Well, we've been working with a hypothesis test that looks like this, right? The lack of effect goes in the null hypothesis, and the expected effect for our one-tailed test here goes in the alternate hypothesis. So since we expect beta 2 to be negative, everything else goes in the null hypothesis. But remember what we talked about. We can also write the null hypothesis as beta 2 equals 0, accounting for the fact of what do we do when we have the sign wrong, which probably we don't in this case. Now, beta 1 and beta 3. What's the expected signs here? Well, again, these are substitutes, so as the price of a substitute goes up, if 12 packs get more expensive and 30 packs get more expensive, so if price goes up, then don't you think people would buy more 18 packs, holding all else constant, right? Because when we change the price of 12 packs and 30 packs, we're holding the price of 18 packs constant. So more sales of 18 packs means the sign is positive. So what's our hypothesis test? Again, we have a directional hypothesis, so it's a one-tailed test. Remember, the no effect goes in the null hypothesis. So if we're looking at beta 1 with the expectation that it's positive, right, our directional hypothesis goes in the alternate hypothesis and everything else goes in the null hypothesis. But remember, we can rewrite that null hypothesis as simply being beta 1 equals 0. Because again, that allows us to reject the null when we have the wrong sign. So in regression, it's not uncommon to write it beta 1 equals 0 for the null, leaving the alternate hypothesis beta 1 greater than 0. Beta 3, we also expect to be positive, so we would set up our hypothesis tests the same way. So let's take a look. Do we have the expected signs? Well, we said that the price of 18 packs should be negative, right? Price goes up, we sell less. And then the price of the substitutes should have a positive effect, because when the substitutes get more expensive, we sell more 18 packs. And we do have the right signs, right? We expected the substitutes to have a positive coefficient and the price of 18 packs itself to have a negative coefficient. All right, so we do have the right sign, but we haven't tested for significance. So we need to ask, are these statistically significant? And remember, we have two methods, the t-test or p-values, which clearly are related. You can't get one answer with the t-test and another answer with the p-value. So if you are running a test and you're like, wait, if I use the t-statistic, I would reject the null, but with the p-value, I fail to reject the null. Not possible. You've made an error, so go back and take a look. All right, so remember, if we're using our t-test, we need our degrees of freedom. So we have to know our number of observations, which we do right there. 52 is our number of observations. So let's first look at doing a t-test using our t-table, and let's start with price of 18 packs. Now remember, something is significant if the t-statistic is greater than the critical t, but technically we need to have the right sign in a directional hypothesis. However, in regression analysis, if you get the wrong sign but your result is still highly significant, if it was the other sign, we would still reject the null. So second thing, remember, you see the absolute value of the t-statistic. Remember, that's because our t-critical comes from our t-table, which is only the upper tail. It's only positive numbers. So we just take the absolute value of the t-statistic because look at price 18. If you have a negative coefficient, you have a negative t-stat. Take the absolute value, compare it to the critical t. So we need to find the t-critical from our t-table. Let's assume 95% confidence. Remember what that means. That means we only want a 5% chance of making a type 1 error where we reject the null when it's actually true. We need to calculate our degrees of freedom, and for regression, our degrees of freedom is n minus k minus 1. N is number of observations, minus k, our explanatory variables, not including our dependent variable, but just our explanatory variables. We have 3 minus 1. So we have 48 degrees of freedom. Now, the Excel output gives us our t-statistic of 22.6, right? That just came from our regression output. I'm taking the absolute value because, again, the t-tables are always expressed in the positive. And if I look at my t-table, I'm going to have a t-critical of 1.697. So in a second, we'll just take a look at the t-table to make sure I've gotten the right t-critical, but let's determine the result here. We have a t-statistic that's huge, right? 22.6. It's far greater than the t-critical, 1.697. So do we all agree we have a highly significant result at 95% confidence? And in fact, you could do 99% confidence. You could do 99.9% confidence, and you're going to see that you can pass those t-tests. You're going to reject the null as well. Quick reminder, how did I get my t-statistic? Notice here that we have a one-tailed t-test, but we're doing a one-tailed t-test. Rather, this is a one-tailed t-table, and we're doing a one-tailed t-test. So all I have to do, if I want to be 95% significant or confident, then my 95% significance level has an alpha of 0.05. I go to the table, look in that column. So again, I don't have to do anything because this is a one-tailed test and my table is set up for a one-tailed test. So we have 48 degrees of freedom, and so I'm going to use the closest degrees of freedom, which is 30, and we have a critical T of 1.697. So that's where I got that from. All right, now we need to interpret this. So just doing the t-test isn't enough. We now need to interpret, but to do that we need to use the coefficients. So we see for each additional $1 increase in price of 18 packs, sales fall by 6.33 units. So be clear, we use the t-statistic and the p-values to determine significance, but when we interpret, we have to go to the coefficient. But our interpretation is holding all else constant. And what are we holding constant here in our very simple model? We're holding constant the price of substitutes. So don't forget that, holding all else constant when you interpret. Now, let's look at price 30. We have a significant result if, again, our t-stat is greater than our critical t and technically has the expected sign, which it does. But remember, if our sign is wrong, we can still claim a significant result. We just need to say, look, I have the sign wrong. So again, we need to find that critical t at the 95% confidence level, which we already have because, again, we're running a one-tailed test here as well. We've got our 48 degrees of freedom. So our t statistic, which comes from the table right here from our Excel output, 3.16 from our regression output. Compare that to our critical t, which comes from our t distribution table, 1.697. Do we agree? We do have a significant result at the 95% level of confidence. But you could also see if it's significant at the 99% confidence level too. So don't just stop there. You might want to say, hey, can I find a stronger result than this? Can I make a stronger conclusion? So let's ask, would it be significant at the 99% confidence level? Well, again, our t statistic is 3.16 from our regression output, and our critical t, well, we need to go to our table, but here, again, if we want to be 99% confidence, we're at the 99% significance level, then our alpha is 0.01. Again, we have a one-tailed test, and our table's already set up for a one-tailed test, so we don't need to do anything there because we have that positive expected sign. So we just need to read the table with degrees of freedom of 48. Let's look at the closest degrees of freedom, which is 30. We have a critical t of 2.457. So let's add that here. We have a t statistic of 3.16 and a critical t of 2.457. And this is a result that is significant at the 99% confidence level. So don't just stop at the 95% level. Ask, can I claim a stronger result? And in this case, we can. All right. So let's interpret. Again, don't forget, we need to go to the coefficient to interpret. So for each additional $1 increase in the price of 30 packs, we see that the sales of 18 packs increases by 2.47. So if we increase the price of the substitute, people are going to switch to buying 18 packs and we're going to sell more. And so remember, our coefficient is always measured for an additional 1 unit increase. Okay, 1 unit increase. So a 1 unit increase in this case would be $1. Don't forget, again, holding all else constant. Now let's look at our p-values, because remember, that's a shortcut. Your p-value measures the evidence against the null hypothesis, or in favor of the alternative hypothesis. So your p-value is asking, how likely is it that our data came from random chance? So it's the probability of observing this effect in our sample if H0 is actually true. So if the null hypothesis is actually true, how likely is it we would have made an error, that we would have gotten this result? So what the p-value is measuring is the chance of a type 1 error. Remember what a type 1 error is? We reject the null hypothesis when it's actually true. We reject the null when it's actually true. So we see that price 18 has a p-value of 0.000. So that means basically there's no chance that we make a type 1 error. In other words, there's no chance that we observe this in our sample when H0 is actually true. Now, let me remind you here at this point that p-values are expressed for two-tailed tests. Now, we can also say that this result is significant at the 99.9% level of confidence, right? Because I have a p-value of 0.000, meaning that the chance of making a type 1 error is basically 0. And if the chance of error is basically 0, then I have a highly significant result. It's significant at the 99.9% level as well. Now, I've made up these results. What if our results for price 12 looked like this instead? And I've just made this up and pasted some numbers over. So we have a t statistic of 1.279. Now our critical t, if we want to be 95% confident, is 1.697. And if we only want to be 90% confident, it's 1.310. So do we agree that this result wouldn't be statistically significant even at the 90% confidence level? And guys, a 90% confidence level is not a particularly strong result. I mean, it might kind of hint at a result, but you don't want a 10% chance of error, right? So does everyone agree that if this was the data, the output, price 12 would not be statistically significant? And we also see that with a p-value of 0.114. It would only be significant at the 88.6% level. So in this case, we would fail to reject the null hypothesis that beta is less than or equal to 0. Remember, we can express that as the null hypothesis beta equals 0. So basically what we're saying is we're failing to reject that this is something statistically different from 0. Now, this means our chance of making a type 1 error is pretty large. And so there's not enough evidence to claim that we can reject the null hypothesis. And as we just said, we can't claim that beta, our coefficient, is not equal to 0 or, equal to a negative number. So we need to be careful how we interpret a statistically insignificant result. We don't want to say, oh, for every $1 increase, we have a coefficient of 2.016, so sales increased by 2.016, but it's not significant. That makes no sense. So understand, everyone look at that coefficient column for a second for price 12. We're basically saying, yeah, we see from our Excel output 2.016, but we can't claim that's not due to chance. We can't claim that that's really significantly different than 0. So we're going to fail to reject the null. So, guys, in this lecture, we moved from simple regression to multiple regression, and we added control variables to hold other influences constant, so holding all else constant. When we look at our regression results, we want to see if the sign is consistent with expectations, right? If we have them, we may not have expectations, and then we're running two-tailed tests. So remember, this connects to our hypothesis test, one-tailed versus two-tailed test. We can also use the p-values to determine significance, and remember that's a shortcut. Remember the p-value is giving us our actual chance of making a type 1 error. So our confidence level tells us the chance of making an error we're willing to accept. So 95% confident, I'm saying, hey, I'm willing to accept a 5% chance of error. But the p-value tells us what we actually have. So I'm willing to accept 5% chance of error, but I only have 2% chance of a type 1 error. Okay, that's a solid result, right? But we can also use our t-table to conduct our t-tests as we have, and we've done both in this case. Remember, it's important to understand how to use a t-table and not just memorize how to look at a p-value, although you do need to understand that as well. If you understand a t-test, then you can conduct other tests that work the same way. So in the next lecture, we're going to add on another element. We're going to talk about incorporating dummy variables. And so we're going to add just a little bit of sophistication. It is really important that you understand the basics of running a regression, testing for significance using the t-table or using the p-value. Make sure you can do both, and you need to be able to interpret. And remember, our interpretation is always for a 1-unit change. All right, let me know if you have any questions at all. Thanks for listening. I hope you have a fantastic day.